So we just came up with this rule for differential equations, and now we're going to talk about how to solve it. So again, I have x double prime minus 6x prime plus 9x equals 0. I know that my x1 is c1e to the 3t. The question is, what is my x2 equal to? What is the second solution, the second linearly independent solution? Well, I'm going to tell you, and then I'm going to show you at least why it makes sense. So it's super simple. All I do is take x2 equal to the same thing, c2, e to the 3t, but I tack a t on. I put a t in front of it. So I increase that power by 1. This really had a t to the 0. Now this has a t to the 1 on it. And I will show you that it fits in a little bit. And I'm going to give you some intuition as to why. But let me show you another example. So remember, the characteristic equation for this was r minus 3 squared was 0. What if and I'm not going to give you the differential equation. Say we had, say the characteristic equation was r minus 3, but instead of squared, it was cubed, right? So I would have, that means that I would have a repeated root. It's like doubly repeated, right? So I have r equals 3, 3, 3. Question is, what would we do? What would my solution be? Well, I think you should see that the first one, x1, x of t, is going to be c1 e to the 3t. That's my x1, plus c2 times something, plus c3 times something. Well, what's c2 going to get multiplied? T e to the 3t. And then for this one, I have to take e to the 3t, because it has to have that in it. And then what do I put on it? How do I make this guy right here linearly independent from that and from that, right? It has to be linearly independent from those individual pieces. Well, you probably guessed it. I just put a t squared, right? That'll work every time. So let's talk about why a little bit here. So why is this? I could prove it with A's and B's, but that doesn't really, like, I could prove to you that let's see, I could prove that x double prime plus 2ax prime plus a squared x equals 0. I could prove to you that the solution to that thing would be x of t is c1 e to the a t but negative plus c2 t e to the a t but negative. I just tack this t on. I could prove to you that that's true, but that doesn't really help me understand why. I will show you why here, or at least give you like a intuitive reason as to why. Say I had x double or x triple prime equals 0, right? So it is a linear third order differential equation, but all the terms below the triple prime are just 0, or just have 0 as their coefficients. Instead of you can solve this directly with like calculus 1, right? With calc AB. But let's think about it from a characteristic equation perspective. Well, if I did my characteristic equation, I would get r cubed for the x triple prime, and then it would be equal to 0. Well, what is the root? Well, that gives me r equals 0, 0, 0. So notice this thing has a repeated root of 0, and it's repeated 3 times. So what would my solution be? It would be x equals c1 e to the 0t. Actually, I'm going to write x1 equals c1 e to the 0t. That would be the first solution. Well, what is e to the 0t? It's just e to the 0, which is 1, right? So this is really just another way of saying that x1 is c1, because it's c1 times e to the 0, which is 1. You should understand that. The question is, what is x2 equal to? And what is x3 equal to? Because when I add those three up, x1, x2, x3, I should get my x of t, right? So let's inspect it. Well, here, let's use the rule, and then let's see why it happens because of calculus, right? Well, what would my rule here be? I would tack this t on, right? So I would get x2 is going to be c2 times a t. And then x3 is c3 times a t, but I got to make it linearly independent from the t, so I make it squared, right? So my solution should be x of t is c1 plus c2t plus c3t squared. That's what I should get if I do like regular calculus to this. So let me show you how we can get a solution to this thing just using straight up integration. X triple prime, oops, equals 0. And I better get that right there. Well, let me integrate that. Let me integrate it once. X double prime, because if I integrate the prime, equals, what do I got on the right side? I'm not going to do a C1. I'm going to call this C3. You'll see why. I just integrate a 0, I get a constant, right? Now let's integrate again. What do I get? X prime equals, now I got to do C3. It's got to get the independent variable here. So in this case, t is our independent variable. So I get a t, but then I got to add a new constant. I'm going to call this C2. Let me integrate again. This gives me x of t on the left side equals, I get C3 over 2 times t squared plus C2 times t plus another constant, C1. Well, I would argue that this guy right here is really just, what's C3, a constant divided by 2? It's really a constant, right? So I would argue that we could just write this, if we do some like renaming and back tagging, we could get rid of the 2. So notice that is exactly what we have right here. I've got over here C3 t squared, that's this thing, t squared, plus C2t, this, plus C1 right there. So I was able to show that my rule for repeated roots matches what we get here when we do this integration. And this will work 100% of the time when you have a repeated root. So let's do an example. Let's take, let's take x double prime minus 2x prime plus x is equal to 0. I'd like you to try to solve that. Hit pause, do it. Okay, I get r squared minus 2r plus 1 equals 0. That's r minus 1 squared equals 0. R equals 1 comma 1. That gives me x equals c1 e to the t plus c2 t e to the t. Now, I'm going to show you that it has to fit this equation here. So, copy that guy over here. Now, I'm going to take the derivative, x prime is equal to, all right, I get c1 e to the t plus, I got to use product rule right here. So the derivative first is, derivative of t is 1, so I get c2 times 1 times e to the t plus c2 times the derivative of the second e to the t is just e to the t times the t is the exact same term. So I get c2 t e to the t. X double prime is equal to, well, this first row, the first column right here, that just derives to itself, c1 e to the t, plus, let's see, c2 e to the t just derives back to itself, and then plus didn't we just take the derivative of this thing? C2e to the t was this thing. It derived to this plus this. So I get plus C2 e to the t. That's the first part of product rule. Plus the second part of product rule gives me C2 t e to the t. Now, let's confirm that this works. In order to do this, I'm going to break it into two parts. This is all the C1 pieces. Notice if I plug that into this equation right here, the middle row gets doubled. Or the middle column row, the middle row there gets doubled. So I will have two of these, but they're negative. I should put this negative here. So that will cancel with this and this because those guys have a coefficient of 1. Now let's look at this mess over here. I've got that guy. I think you should see that it works out. We'll use a highlighter. This guy would get this -2. And then would get multiplied, or then would get added to this and this. So this term right here cancels with those guys, right? And then look at this. This thing, because this is hard to explain. This thing, it just stayed the same all the way through, right? It did the same thing that this did. It just did the same thing all the way through. So this guy, these guys right here, this, and this, they have the same form as this, and this. And that is totally because of how product rule works. But these guys will cancel out in the same way that these will. If you had something like say I had my, all right, sure, let's take this one up here. Say I had this one right here, right? My solution would be x of t equals c1 e to the 3t plus c2 times t e to the 3t. I would argue that the chain rule on this piece right here, if I were to do it 3 times, would be the same as the chain rule on this piece 3 times in that same structure down below. And I would get these pieces, if they fit, then these pieces will fit the equation in the exact same way. And then if you mess with those extra little pieces right here, those guys will also cancel perfectly the same way that I got here. I would have the same structure. These cancel for the same reason that these cancel, because they appear from the same derivative, and then these guys will also cancel. And that's what I was saying earlier with A's, right? If you were to do this and plug this through, right, then it would work out perfectly the way that this has here. And that's why we tack this t on when we get our repeated roots.